In 1915, on the 25th of November, Albert Einstein submitted his final field equations to the Prussian Academy of Sciences. He had spent a decade chasing them. When he finally held the completed system on paper, he later wrote that he was so overcome he could not sleep for several days. The equations describe something so radical that even Einstein refused to believe it. The universe is not static. It is not a fixed stage on which stars burn and planets orbit. It is a dynamic entity, something that can stretch, warp, and perhaps, most terrifyingly, collapse. Einstein introduced a fudge factor, a cosmological constant, just to hold the universe still. As physicist George Gamow later recalled, Einstein called it the greatest blunder of his life. But what if the blunder wasn't the constant? What if the blunder was his instinct, our instinct, that the universe wants to stay put? By the end of this video, we will have looked squarely at one of the most unsettling possibilities in all of cosmology. Not that the universe ends in a slow, cold fade, but that it might already be curling back on itself, like a breath held too long, ready to exhale everything into a single, infinitely hot point. Let's name the thing we're actually talking about, the Big Crunch. In technical terms, it refers to a cosmological scenario in which the universe's expansion eventually slows, halts, and reverses, drawing all matter, all energy, all space-time itself, back into a state of near infinite density, a gravitational collapse of everything, the mirror image of the Big Bang, played in reverse. Now, here is where the pattern interrupts lives. Most of us have been quietly told, somewhere between a documentary and a university lecture, that the universe is expanding and will expand forever. That the Big Crunch is an old idea, a relic of 20th century physics, effectively disproven. And that is very nearly true. Observations of distant Type 1a, supernovae, first published in 1998, revealed that the universe's expansion is not slowing. It is accelerating. Dark energy appears to push everything apart faster and faster. But here is the catch. We do not know what dark energy is. We measure its effect. We do not understand its nature. And the moment you acknowledge that, the word disproven starts to feel a little less comfortable. The Big Crunch is not a closed case. It is a case where the only witness, dark energy, keeps changing its testimony. In 1922, Russian mathematician Alexander Friedmann derived solutions to Einstein's field equations that Einstein himself initially dismissed as a mathematical error. Friedmann's solutions described a universe that could be open, flat, or closed. Think of it this way. And this is an analogy that has been used to explain Friedmann's solutions ever since. Imagine inflating a balloon. As you blow air in, the rubber surface expands. Every dot on the surface moves away from every other dot. Now imagine the balloon has a fixed amount of elasticity. If you blow too much air in, the rubber stretches thin, and eventually, that's one scenario. But what if the rubber has enough tension to push back? What if gravitational pull, the elastic memory of the material, is strong enough to overcome the expansion? Then the balloon doesn't pop. It reaches a maximum size, pauses for a fraction of eternity, and starts contracting. Friedmann's closed universe model was mathematically rigorous. It predicted a universe with a beginning, a peak, and an end. Not in metaphor, but in the geometry of space-time itself. What Friedmann couldn't know, sitting in Petrograd in 1922, was which type of balloon we actually live in. We promised to look at whether the universe might already be falling inward. And here is where the paradox bites hardest. The critical question in cosmology has always been about density. There is a value. Physicists call it omega, or the density parameter, that compares the actual density of the universe to a critical threshold. If omega is greater than 1, Gravity wins. Expansion stalls, reverses, collapses. If omega is less than 1, the universe is geometrically open. It expands forever. If omega equals exactly 1, the universe is flat. It expands forever, but just barely. Current measurements from the cosmic microwave background, the faint thermal afterglow of the Big Bang, mapped with extraordinary precision by the Planck satellite mission, place omega at approximately 1, flat. The universe appears geometrically flat to within a fraction of a percent. That is the reassuring answer. We're flat. We expand forever. The Big Crunch is not our fate. Here is the second turn. Flatness is only a present observation. Dark energy's behavior over cosmological timescales remains, by the Planck collaboration's own admission, deeply unresolved. Its strength is characterized by a parameter physicists write as W, the equation of state. If W equals -1, dark energy is a true cosmological constant, stable, eternal, driving gentle expansion forever. If W drifts above -1, even slightly, expansion could eventually slow. And if W drifts below -1, we face the inverse catastrophe, not a crunch, but a rip. The cosmos torn apart at the subatomic level. We currently cannot distinguish these futures with certainty. We are orbiting the answer, not holding it. At this point, a very reasonable objection arises. If the universe is accelerating, isn't the Big Crunch simply ruled out by observation? The galaxies are flying apart faster every billion years. What could possibly reverse that? The objection is logical, and it's also exactly where our understanding is most fragile. The acceleration we observe is a local snapshot. Local in cosmological terms, meaning the last few billion years of a 13.8 billion year history. We are extrapolating an enormous conclusion from a relatively narrow observational window. And physical models of dark energy are, at this moment, actively contested. A class of cosmological models known as quintessence models replace the cosmological constant with a dynamic scalar field, a kind of energy that can change its value over time. In some quintessence scenarios, the dark energy field evolves from its current repulsive dominance to a weaker state, or even to a state that assists gravitational collapse on the grandest scales. These are not fringe proposals. They appear in the same peer-reviewed literature that produced the accelerating universe discovery. The debate is real, it is ongoing, and it is unresolved. What's even more destabilizing? We infer the existence and properties of dark energy almost entirely through its gravitational effects on the expansion rate. We have no direct detection of it. We have a behavior pattern associated with something we can't see, measure directly, or explain from first principles. That's the foundation on which our confidence in forever expanding actually rests. The Greeks had a word for it, apeiron, the boundless, the indefinite. Anaximander of Miletus, writing in roughly the 6th century BC, proposed that all things emerge from an infinite, undifferentiated source, and crucially, must return to it. Not as a religious claim, as a philosophical necessity. Everything that is individuated, he argued, must eventually be reabsorbed into the formless origin. We usually consider this quaint cosmology, but it keeps surfacing in formal physics. The cyclic cosmology championed by physicists Roger Penrose and Paul Steinhardt, in separate competing models, draws on exactly this intuition, that the universe may not have a single birth and a single death, but instead passes through cycles. In Penrose's conformal cyclic cosmology, each aeon ends in a state similar to the Big Crunch, or, in his formulation, a smooth cold terminal state that is conformally equivalent to a new Big Bang. In the ekpyrotic model proposed by Steinhardt and collaborators, two brains collide cyclically in a higher dimensional space. The point is not that any of these models is correct. The point is that some of the most rigorous minds in theoretical physics cannot fully dismiss the idea of cosmic return. The Big Crunch, or something structurally similar to it, keeps surviving every attempt to bury it. Stephen Hawking, in a widely cited remark, put it this way, and I want to let this sit for a moment. The universe doesn't allow perfection. And by that he meant something specific. Every physical system contains fluctuations, asymmetries, seeds of its own undoing. A perfectly expanding universe, held in perfect balance by a perfectly constant dark energy, with a perfectly flat geometry. That's not a description of nature. That's a description of a toy. The universe, as best we understand it, is a system that began in an extraordinary deviation from equilibrium, a point of infinite density and temperature, and has been spending its energy budget ever since. The question, will it collapse, is, in a very real sense, the question. Has it been spending faster than it earns? We don't know. In 1917, Willem de Sitter published an alternative solution to Einstein's field equations, a universe with no matter at all, only the cosmological constant. It was mathematically consistent. It showed that expansion was possible, even without matter driving it. For a decade, the debate between Einstein's static model and de Sitter's expanding empty model was the central intellectual contest in cosmology. Then in 1929, Edwin Hubble published observational data showing that galaxies were receding from us at velocities proportional to their distances. The universe was expanding. Both Einstein and de Sitter were partially right and substantially wrong in ways they hadn't anticipated. The lesson here is not that old ideas were naive. The lesson is that within a span of 12 years, from 1917 to 1929, the reigning cosmological consensus was overturned by a single observational paper. What we believed to be the settled geometry of the cosmos was simply the best model we could build with the instruments we had. We have better instruments today, but we are still building models, and every model carries the ghost of an assumption we haven't yet thought to question. What assumption are we protecting right now without realizing it? The most active frontier in answering the Big Crunch question is not theoretical, it's observational. A suite of current and near-future surveys are attempting to pin down the nature of dark energy with a precision that was unimaginable a generation ago. The Dark Energy Spectroscopic Instrument, DESI, began full survey operations, and in its first major data release in 2024, suggested that dark energy may not be constant. The hints are subtle and not yet definitive, but the data raises the possibility that the density of dark energy is evolving over cosmic time, which would have profound implications for whether expansion continues, stalls, or reverses. The Euclid Space Telescope, launched by the European Space Agency in 2023, is building a three-dimensional map of the universe's large-scale structure, reaching back 10 billion years. Specifically designed to measure the evolution of W over cosmic time. If these surveys find that W is drifting, even slightly, the cosmological landscape will shift beneath us. A universe that was definitely expanding forever becomes something less certain. The models that allow for eventual recollapse return from the archive. We have built the most extraordinary instruments in human history to answer a question that philosophers articulated before the wheel was invented. Where does everything go? The answer is still pending. Go back to Einstein in 1915, a man who had just written the equations of the cosmos and then immediately smoothed them over because he couldn't tolerate what they implied. He introduced the cosmological constant to prevent a universe that moves. He needed stillness, that instinct, the need for stillness, for permanence, for a cosmos that simply is rather than one that goes somewhere, is very human. We build civilizations on the assumption that the stage will keep holding us. We plan centuries ahead on the assumption that the room will still be there. But the equations don't care about our comfort. Friedman's solutions in 1922, the supernova data of 1998, the DESI results of 2024, they all point to the same unsettling truth. The universe has a direction. It is not a backdrop. It is a process. Whether that process ends in a big crunch, in an unimaginable compression of all light, all matter, all distance into a single burning point, or in a slow fade, or in a tear, or in something we haven't named yet, we genuinely don't know. What we do know is this. Every time we've been certain about the fate of the cosmos has quietly arranged a surprise. Maybe that's the most honest thing cosmology has ever taught us. Not what the universe will do, but how thoroughly it has humbled everyone who thought they already knew.